Hello, my name is Israt Sharmin Dola, and today I'll be presenting our research work titled Human Pose Estimation using Automated Multi-Camera Calibration. To begin, let me briefly introduce the core idea behind this research. Pose estimation refers to detecting the 3D joint positions of a human body from camera images or videos. In other words, it's about figuring out where each joint is located in space using only visual input. This capability has wide applications in animation, gaming, fitness, healthcare, virtual or augmented reality, and many more. But in our case, we are especially interested in its use for human-robot collaboration. Here, pose estimation allows robots to understand human movements, avoid collisions, and assist effectively in shared tasks. However, there are still a few key challenges that we face. For example, real-world setups like construction sites are dynamic in nature. Cameras often need to be moved or repositioned as tasks and layouts change. But every time you move a camera, change its number, or replace it, the entire system needs to be recalibrated, which is manual, time-consuming, and prone to errors. These limitations are exactly what motivated our research to develop a system that can adapt to dynamic environments without requiring manual recalibration. Now, for a system to estimate human pose accurately, it first needs to know exactly where each camera is positioned and how it's oriented in space. That's where camera calibration comes in. It aligns all the individual camera views to a common global coordinate system, enabling us to derive 3D joint positions from 2D images. Researchers initially explored monocular systems using depth cameras or wearables. While convenient, these often suffer from limited body visibility, and depth sensors vary greatly in their accuracy depending on the type used. Multi-camera systems offer a better solution as they capture the body from multiple angles and provide full upper and lower body visibility. However, the trade-off is that each camera must be manually calibrated beforehand. And if you move even one camera or change the setup, the entire system needs to be recalibrated from scratch. Traditionally, this calibration uses a reference object with a known spatial structure like a checkerboard, where the exact position and orientation must be predefined. Some researchers have tried automating this with robotic arms or precision sliders, but these setups require highly controlled environments and specialized hardware, making them expensive and impractical for field use. To address these challenges, our research has two main objectives. First, to automate camera calibration, eliminating manual setup so cameras can be added or moved freely, making the system adaptable to dynamic environments like construction sites. And second, to improve the accuracy of 3D human joint estimation by fusing data from multiple cameras for better results. To achieve this, our system estimates several variables: the 3D joint positions of the human body, each camera's position and orientation, and their horizontal and vertical fields of view. The setup will look similar to this. Multiple cameras with their own parameters observe the same human joints from different angles, providing full visibility of the upper and lower body. To achieve accurate 3D joint estimation, we define specific inputs and observables in this setup. Our inputs are the camera parameters. Each camera's 3D position, orientation angles, and fields of view. The observables are the 2D joint locations detected in each image. Using these, our framework outputs the 3D joint positions of the human body in a unified global coordinate system. This is an overview of our proposed framework, which has three main components: a vision-based pipeline for 2D joint detection, a marker detection and alignment to establish a global coordinate system, and an extended Kalman filter that simultaneously estimates both the 3D human joints and the camera parameters. Let's now walk through each component in detail. We used MediaPipe's built-in pose alignment to detect 2D joint positions. We have selected 15 major joints such as the shoulders, elbows, hips, knees, and ankles from the 33 landmarks and have retained only those with a confidence score above 0.8 for reliable 2D coordinates. These filter joint measurements are then used as the actual observations in the next stage of our framework. Next, to establish a global reference frame for all camera views, we use a marker-based approach. In principle, any marker with unique trackable features could be used. We chose Arco markers because of their unique binary patterns, identifiable IDs, high detection accuracy, and resilience to moderate lighting variations. By detecting these markers in each camera's image, we are able to align all camera views into a shared global coordinate system. Now that we have extracted 2D joint landmarks and established a global reference frame, we use an extended Kalman filter to estimate both human joint positions and camera parameters. The EKF operates on a unified state vector containing the 3D joint coordinates and the camera parameters. It follows a two-step process: a prediction step to estimate state changes over time, and a correction step to refine these estimates using new 2D joint and marker measurements. This enables continuous and adaptive updates, ensuring accurate joint and camera estimation even in dynamic environments. At each time step, we first predict how joint positions evolve using a random walk model, adding Gaussian noise to the current estimate. We then project these predicted 3D joints onto each camera's 2D image plane. This involves transforming joints from global to local camera coordinates and using a pinhole camera model to calculate their 2D pixel positions based on the camera's fields of view. This gives us the expected 2D joint locations for each camera, which are then compared to the actual observations. Based on the discrepancy, the EKF corrects the estimates. This prediction correction cycle repeats over time, gradually refining both joint positions and camera parameters until the outputs converge. For our experiments, we used VBots because it provides a controlled environment to evaluate our framework effectively. We set up 4 cameras around a pedestrian proto-model with 15 joints and placed a 5 centimeter Arco marker for calibration. Each camera captured images as 640 by 640 resolution. We ran 30 trials with this setup and used RMS error as our main evaluation matrix. Here are the results from our 30 trials. The plots show the error convergence for our 4 key parameters. In the top left, we see the joint position distance error. It starts around 2 meters and quickly drops below 0.25 meters within the first 50 iterations, stabilizing at an average error of around 0.18 meters. The top right plot shows camera position error. It begins above 6 meters but steadily decreases to below 0.5 meters with a final mean error of 0.32 meters. On the bottom left is the camera orientation error. Initially, it's over 40 degrees, but it quickly reduces to around 10 to 15 degrees with a mean error of about 11 degrees. Finally, the bottom right shows the camera field of view estimation error. It starts between 15 to 18 degrees and gradually converges to below 5 degrees with a mean error around 9 degrees. We also notice some small fluctuations. These are expected as the EKF continuously updates its estimates as new 2D joint and marker measurements are received. Each update can temporarily shift the estimate before it stabilizes again. It shows that the filter remains responsive and gradually reduces fluctuations as it converges. Overall, these results demonstrate that our framework converges quickly, typically within the first 100 to 150 iterations, and achieves reliable estimation across all parameters, making it practical for dynamic environments. To conclude, our framework successfully estimates 3D human joint positions while automatically calibrating multiple camera parameters without needing any prior knowledge of object positions, depth sensors, or predefined motions. Looking ahead, we plan to extend this system to real-world deployments, explore markerless calibration setups, estimate additional camera parameters, and expand it to multi-person tracking and activity recognition. These are some of the key references I used for this presentation, and the complete list can be found in the full paper. Thank you for your time and attention. I'd be happy to answer any questions.